Hi everyone, welcome to Distributed SQL Summit Asia 2022. This is the second year, in fact, the second consecutive year that we are hosting this industry event in Asia. Now, last year we had 750 people join us for the event. Can anyone guess how many people we have this year? We have over 2,000 people joining from 41 countries around the world. That's amazing. And I believe that that is a testament to the growing demand and interest in distributed SQL. In fact, at Yugabyte, we are seeing this growing demand from organizations around the world for a modern cloud-native transactional database. And this is just the start. We are in the first innings of what is probably going to be a decade-long transformation that is already underway. Now, over the next couple of days, you will hear from organizations that are using distributed SQL for their mission-critical applications, as well as from technology partners and solution architects deploying distributed SQL for a variety of use cases. I have a few reminders from the organizing team to make sure that you get the most out of this event. So let's go over them. Please use the chat feature in the main stage for general conversations about the conference. Speakers will generally hang out after each session. So if you have any questions, post them in the chat and they'll get answered at the end of the session. All sessions will be available on demand after the event is over, so you can go and watch the recordings later. Lots of prize giveaways and swag to be won, so keep an eye on the chat as well as during the closing keynotes to find out more. Follow along on social channels using hashtag DSS Asia and hashtag Distributed SQL. In fact, if you want to post, use those hashtags so others can find you. And finally, and most importantly, join our community Slack channel, folks. That is where a lot of the conversations happen in the community. We're going to be posting the instructions in the chat window right now. So definitely join us there, both during and after the conference. We're going to be having a lot of discussions there. Now, without further ado, let's start this event with the opening keynote by Karthik Ranganathan, Yugabyte's CTO and co-founder. I'm going to set the context here. Application modernization and the shift to microservices is driving the need for a modern cloud-native database. Karthik is going to talk about the life of one such cloud-native application from the perspective of the data layer. Okay, Karthik, over to you.
Thanks, Sudha. Thank you for the great intro, and thanks all of you for tuning in. Really excited to see all of you guys come here. Very excited by the fact that we're seeing huge growth and huge interest in distributed SQL. As Sudha said, 750 people to over 2,000 this year. Amazing. Let's keep it going. Okay, so without further ado, let me jump right in. Well, a couple of words of caution though, even before we get started. One of the things I personally hated about most of the keynotes is that they're just too serious, right? So this year, we've tried to make the keynote really fun. Now, remember that there's a healthy dose of sarcasm and self-deprecating fun that we're making along the lines of, the Silicon Valley episode where we make fun of ourselves. So it's not meant to be serious, but yet it's meant to convey certain points. Okay, so the title for the keynote this year is The Biography of a Modern Application. So we're going to look at the life cycle of a modern application from birth to where it gets really big, right? And specifically from the perspective of data, rather that way, from the perspective of data. Okay, well, let's take a look at an app's life, right? Like what really happens for a modern application? Well, an app births in the cloud, right? And then, you pretty quickly know, is it really, you improve it, you keep listening to your users, you build in the features, and then it starts getting ready to grow. A lot of people like it and so on. And then, then you hit the kind of the teenage years where you have to make sure your app is running all the time. It deals with outages, everything functions smoothly. And then you reach a stage when it gets really successful and you have to have, planned scaling, unplanned scaling, sudden bursty activity, so on and so forth. And finally, you start going global, right? Well, these are the life cycle stages of a typical cloud-native user-facing application. But rather than put it abstractly, this entire keynote is modeled along a single theme: show, don't tell. So, the other thing that I didn't like about people doing keynotes is they say a lot and it's difficult to absorb a lot of stuff. So this keynote, we have a lot of demos interspersed where we don't just tell you how things should work, we actually show you. So in that spirit, rather than just tell you this is the life cycle of an app, let's actually go through it. Let's show it. An app always starts with an idea, right? It's a bright idea or not, but time will tell. But anyway, it always starts with an idea. Well, in our case, the idea is to come up with a store, an online store for books. And in fact, everything. It starts with books, but then it becomes everything, right? And a fun trivia fact for all of you users out there. Do you folks know what the largest river in the world is? Well, if you guessed Amazon, that's right, you got it right. And so our aptly named venture for this idea is going to be www.thelargestriver.com. All right, so what are we going to do in this idea, which is about an online shopping experience? Well, if it was happening today, you have to build it and launch it immediately, right? The minute you have an idea, you pretty much have 15 other people trying to do something similar, so you better do it right away. Well, the first thing is to buy the URL, www.thelargestriver.com. And then you pick a microservices architecture. Well, you don't overdo it because you want to move quickly. Come up with some quick wireframe and UX design. We pick AWS as the cloud. And then we pick up an app framework like Spring. And the last choice here is to pick the database. Again, remember, this is from the perspective of data. So how does picking a database look? You obviously have to pick distributed SQL and just start there, right? Wrong. Just because we're doing the keynote doesn't mean that's the right answer. Well, most people simply end up picking Postgres SQL. That's the natural database choice. And no wonder Postgres is indeed the fastest growing database in the world right now. Why do folks pick Postgres? Well, firstly, it has a rich support for a number of different application frameworks like Spring, SQLite, GraphQL, and so on, with an incredible set of database features. It's got a huge developer tool set and ecosystem around it, dbeaver, Table+, Kafka, Presto, Spark, you name it, a ton of others. And it's pretty bulletproof and future-proofed. It's a very extensible database, it's highly open source, and it's really loved and supported by a large community. So, what's to go wrong? Naturally, start with Postgres. Well, pretty soon, now that we've written our app, we've picked everything, we've picked our database, let's say we've launched www.thelargestriver.com. Right? Huge blast off, huge launch. Well, I really hope the car lands on the other side. But anyways, our website did. And our users just love the service. It's growing virally. And pretty soon we have revenue from the app, right? Like people are buying stuff and we're making money. Everything is going great. Fantastic. Well, VCs start knocking on your door and they say, you need to put together a slide deck and an elevator pitch and come talk to us and so on and so forth. And before you know it, you've raised 25 million in Series A, you've got TechCrunch covering you, your elevator pitch is it's the cloud native everything store. Again, fun fact, just like we talked about the largest river being Amazon. Did you folks know that Amazon started as a bookstore and then evolved into an e-commerce store? Well, we're a few years late, but hey, it could happen to us. Let's keep going. So now that we have all of this publicity, that brings even more users to the site, and the VCs that put in the money, they want to see you go big or go home. So the next day, the real work begins. Now that you have money in the bank, well, what are you going to do with it? Well, go home or go big. Let's hire a ton of people, and we are going to architect for zero downtime. That means anybody wanting to buy anything anywhere, well, they should be able to do it. And we're going to have more and more people buy because we're already seeing the growth. So let's prepare for scale sometime in the future. How much scale? Don't know. Will a single node suffice? I don't know. It could be anything, right? So let's keep going. We'll just assume that we've figured out hiring because, hey, how hard can that be? But let's go to the second problem, which is of interest from the data perspective, which is how do you architect for zero downtime? Well, there's a few options. The first option is you can choose asynchronous replication on top of a database like PostgreSQL, which that's what you picked. Well, what is the problem with this approach? It is a challenge to set up, is to maintain and to scale over time. Your application becomes complex because you now have a primary database asynchronously replicating to a replica database, and you need to know which parts you have to read from the primary, which parts from the replica, when the replica gets promoted, which is the data loss scenario, and who promotes it and when, how much data is lost, how does my app really work, when do I fail over back, is my app aware of which gets which, like the replica getting promoted or not? A lot of issues here. So you think long and hard about it and you say, what else is out there? Well, your second option is to set up synchronous replication at the storage layer. If you're using a cloud, that'd be something like Amazon Aurora. If you're using it like on an on-premise data center, it would be a SAN or a NAS, right? Like a NetApp filer. Well, the problems in this case are that your failure is not instantaneous, right? Like when the failure happens, you would need another node to come up and start reading from the disk and warm its cache and be ready to serve. That means it could be an extended outage for the end user, and that could cause drop-offs. And remember, we're going big or we're going home. The second issue with this approach is because you're going to have a lot of people coming in and trying to access and run transactions, the application architecture itself becomes complex on failovers, just like in the previous example. When a node fails, when the primary fails and a replica is picking up, the app should be aware of the fact that it needs to now interact with the replica, or the load balancer should switch something. And if you have a load balancer service, you need to know what is the read endpoint, the write endpoint, a lot of details, right? And finally, things like software upgrades, database software upgrades, instance upgrades, security patching the OS, all of these start getting complex because, it all experiences some form of failover to a different node. And, failover causes a blip in the user experience. And so that means users are constantly getting a poor experience. So you're like, yeah, that's better, but, what else is out there? Well, and then you've attended the Distributed SQL Summit and you remember Distributed SQL. So let's go to synchronous replication that's native to the database. Well, it's operationally really simple because the database just handles the scaling. You just add nodes or you replace nodes one at a time. And it's transparent to the application, the way the whole thing works. There's not a tier of reads, a write, a replica, none of that stuff. And you don't need to deal with data loss at all. It is seamless. Your failover is instant. You can get, what you see is a slightly elevated latency in your application, and that's great. So you're like, awesome, that's the one I want. Let me go with that. Well, your next problem was, how do you architect for scale? Well, you say, okay, option one is I could scale up. I could get a bigger machine, except it limits my scalability. There's a limit to the largest machine I can ever get. It's disruptive. It's really complicated to take another machine, take the data, put it there, switch over the app, a lot of work. And it's not easy to do this all the time. Like your scale could increase and decrease, especially if you're a retailer, you have peak season and not so peak seasons and so on, right? So you're like, okay, what else is out there? Well, your other option is to manually shard PostgreSQL, and you can have different users put into different buckets of PostgreSQL, but this is operationally challenging. You'll have to, kind of architect your application to do this, and it'll take a while. And the whole thing is fragile because when you add a new node, you'll have to redistribute all the shards. You have to do a lot of work in this scenario. So you're like, yeah, nope, not feeling it. I need speed. What else is out there? Well, another often recommended solution is to simply put a lot of caches and replicas and run off of that. Well, firstly, it doesn't solve the right scalability where a lot of users are placing orders and adding to cart. Your application becomes really complex. You need to know what is your primary endpoint, what are your replica endpoints, which queries do I send here versus there, and cache coherence and operationally the whole solution is really hard. So you're like, okay. And once again, you remember that Distributed SQL Summit where they were making a lot of jokes in the keynote. That's the one. Let's go. You think about Distributed SQL Summit and Distributed SQL, and it's easy to scale out and in automatically. The database takes care of it. It's operationally simple, transparent to the applications, and I can scale in and out as I need it. Bingo, that's the one I want, right? And now the practicality kicks in. Yes, let's do it. We are totally ready for Distributed SQL, but wait, is it really that easy to switch from PostgreSQL to a Distributed SQL solution? Will I be stuck there? Is this going to be complicated? Well, you know what? In the show, don't tell style, let's actually take a look at migrating a relatively complex application from PostgreSQL to Distributed SQL. Let's see it in the works.
Hello everyone, welcome to the conference. My name is Denis Magda, the head of developer relations for Yugabyte. Let me introduce you to the demo architecture. What do we have by default? We have a popping-up service of a real-time data stream. The data stream represents sort of New York Stock Exchange. You have like every second different purchases, different stocks, different equities, and all this information is going to be streamed into our Java backend service. The Java backend stores all the trade information into the Postgres database, and also we have archetype SQL management tool to run several SQL operations. So that's what's given. And what would you like to achieve? We want to keep all the components untouched except for the database. We want to migrate from Postgres to a cloud-native YugabyteDB deployment that is resilient and scalable, and we have to achieve it within a few minutes. So let's go straight to the code. My Postgres database is running on a remote machine. If I'm already connected to that database with archetype, let me run this query. For instance, we already have buyers loaded, but we don't have any trades yet. 0. Why don't we have? Because we have to start our backend Java application. Let's do that. For that Java application, we are going to use a special Postgres connection properties. And also we want the application to print different statistics every 5 seconds. They're going to query the trades number and they're going to return the most popular stocks. So let's quickly look at that properties file. Again, that's the remote machine and the Postgres is running locally. So these are my configuration parameters. Now starting this application. The application is going to connect to the PubNub service. So the connection went well. And right now you see that the data is being inserted and also our statistics information is being printed out. We have trades added to the Postgres database and these are the most popular trades. If you go back to archetype and execute the same query here, you can see that the number keeps changing. Excellent. We are streaming data from PubNub. But right now, let's imagine the following situation. You decided that the time has come to migrate from your single node Postgres database to a cloud-native, resilient Yugabyte deployment. So what's the easiest way to do that? I'll show you in a few minutes. So what I've created, I have used Yugabyte platform, the special service/software that lets you to deploy YugabyteDB in your infrastructure. I deployed my 3-node cluster in Google Compute Engine, and every node is located in a dedicated availability zone. So like B, D, and C. I'm doing this purposefully because I want to demonstrate you how the cluster can withstand zone level outages. All right, so let's do this right now. Imagine that you negotiated the maintenance window for your application and you are stopping the application right now. We are using Yugabyte Migrate tool to export schema and data from the Postgres database. And the same tool supports MySQL and Oracle. So let's copy this command. Okay, we connected to Postgres. We have just 2 tables. It's enough for our real-time stream. And we imported everything. Good to go. So next step is to load all this data into my platform cluster. Just to double check, let me use archetype and connect to that platform YugabyteDB deployment. If I run this command right now, it says there is no relation at all because this database is not created. And we don't need to. We are going to use Yugabyte Migrate tool. So first we have to migrate the schema. Okay, we successfully connected. Domain, we use sequences. We certainly have different tables. So right now, rules, functions, aggregates. Usually it takes, let's say, 10-20 seconds. It's done. After that, let's migrate the data. Okay, connected. We are migrating the buyer table, trading, done. All the data is in my Yugabyte database that is deployed in the cloud, Google Compute Engine. Let's double check the same query. I'm running it and I have the trades. Wonderful, right? And right now, let's say that the database migrated successfully and we want to restart our application. I'm going to use the same application, but different configuration parameters. So right now I'm connecting to Yugabyte, and that's my address of one of my Yugabyte nodes. It's private address. I will be able to connect it from my remote platform machine. So let's not wait. Let's quickly run this application. All right, the application connects. We already have stocks. The application connected back to the PubNub, and we keep adding the stocks into the database. Congratulations, the migration went well. Within a few minutes, you migrated your schema and data from your local Postgres database deployment to your cloud-native Yugabyte instance.
Okay, great. So that was simple enough. We were able to move a Postgres application all the way to distributed SQL, YugabyteDB, and we were able to do it easily enough. It was smooth sailing. The migration's done. And just like the boat, where most of it is out of the water, is smooth sailing for a while. You're just like getting users through the wazoo. TheBiggestRiver.com is really taking off. Great, totally great, awesome. You have massive user growth, your product catalog growth, your revenue grows, everything is going well. Until your AWS bill also starts growing really quickly. And you're like, okay, if this keeps going at this rate, well, I'll end up paying AWS more than I ever make, and I'm better off not doing the company at all. Okay, so, another day in the life of a startup, all hands on deck. Let's figure this out. Why is the bill so high? And, there's a lot of things that, your engineering team finds out, but until, aha, eureka, just switching the database to a different instance type saves 40% of the cost. Great. Now I have to change my instance type. Tell me it's just a one-off, right? This is the only time you'd need to do it. Well, the engineer says, no, it depends on the workload and it depends on the machine type. And, in the usual engineering style, you get a really long and complex answer, but all of which makes sense. So the bottom line here is that things like changing your instance type is not a one-off. It could have been a one-off back in the day when, we were running private data centers, but not in the public cloud. Cloud processor generations are getting better all the time, right? If you take a history of the processors, if you just go from 2013 in just one cloud, AWS alone, you see all the generation changes, and look at the price to performance improvements. It's a 40% from C3 to C4, a 25 to 50% C4 to C5, another 40% C5 to C6G, which is Graviton, and then 20% better bandwidth on C7G, which is coming out. And the time window between these releases is actually decreasing, not increasing, which means you have to be ready to make these changes at the drop of a hat. Okay, so what are we going to do about that? Is this going to be a real problem? Well, worry not. With distributed SQL, you can actually change instance types with no disruption to your application. And once again, in the show don't tell style, let's actually take a look at changing instance types on the fly.
And now we've got to the final demo. Imagine that your Yugabyte cloud cluster is already in production, but the application load keeps growing and you need more CPUs. You just want to upgrade your already running instances, and you cannot allow yourself maintenance outages. And you don't need to. With Yugabyte, you can upgrade your infrastructure in the running upgrade fashion, not impacting your application. Let's check it. For this demo, I'm going to use Yugabyte Cloud. Yugabyte Cloud is a fully managed service for YugabyteDB. And my cluster is already prepared and started. I deployed a 3-node cluster in AWS. And every node is running in a separate availability zone, like West to B, to C, and to A. So first thing first, let's right now connect my application to this cluster. I just want to see that the traits are being added, and after that we will change the infrastructure. Getting back to my code, I'm going to use these connectivity properties right now, the same application, but the connection settings are different. That's the public address of my Yugabyte Cloud instance, password and certificate, etc. Let's start this application. The last time we are starting this application. Okay, we connected to PubNub and we started adding the trades. For this cluster, I was not importing data from Postgres. It's like clean. And so, okay, we see the trades are coming, the most popular stocks. And the next step is to go ahead and upgrade our infrastructure. We can do it here. We go to the settings, we find the edit infrastructure button. And let's say that I need 4 CPUs per node, which will result in 12 CPUs in the cluster. I'm just doing this. The infrastructure upgrade is in progress, and you can monitor it here in the activity settings. Let's refresh. Yeah, it's scheduled. You see that the upgrade is in progress, but what I'm interested in is my application. Let's check the code. The code keeps running. The trades are being streamed from PubNub and the trades are being added into my Yugabyte cluster. Wonderful. This is how you can upgrade your infrastructure in real time, live, without any impact on your application. So that's it. Enjoy the rest of the conference.
Excellent. So that was simple. This was really nice. A zero downtime architecture is actually useful in many scenarios, and the needs keep piling up. We just moved to a better instance type, but you could apply the same technique for doing software upgrades, for security patching your OS and refreshing your AMIs to keep the security of your system high, to tolerate node and zone failures and continue serving workloads, in spite of those things happening. So still going like the Energizer Bunny. Awesome. Okay, so with all of that awesome improvement and the general growth, well, you now get another set of venture capitalists coming to you, and now you've got an $80 million Series B, a lot more coverage, a lot more users. And everyone's asking you, okay, how are you going to evolve? Well, your elevator pitch evolves to, we're the cloud native everything store with AIs, NFT, Web3, and all that other stuff without which you wouldn't have gotten that $80 million Series B anyway. Right? And okay, so what is it that you're really worried about? Well, you've gotten a lot of traction, you're growing really fast, success is really sweet, but the scale that it brings is really scary because you just don't know day over day. You get more and more and more users using it. You are really worried about your Black Friday, your Cyber Monday, your seasonal peaks. How are you even going to address this thing? One of the issues with traditional deployments is that you are not able to control the level to which you can expand your cluster and your resources to be able to handle spikes in workloads and then bring it back down after the spikes or the peak season is gone, right? So one of the critical things to remember at this point is you should be in a good cloud native architecture before you reach this point. If you're at the point of scaling for success, you don't want that very success to be the reason for the failure because you cannot handle the scale, right? So something important to keep in mind. Now, on that vein, once again, show, don't tell style, we're going to show how a cluster can scale to handling 1 million transactions per second. That's right, million is the new 1,000. Okay, what you see here on the screen is an example of a cluster that's undergoing huge scale. This is a 75 node cluster, right? 75 nodes behaving as a single logical distributed SQL database. And, it's doing, a ton of operations per second. It's doing about 750,000 read transactions per second at the database level and about 367,000 write operations per second at the database level, making it over 1 million transactions per second. Now, the key takeaway here is that, you never know if your application is going to hit 1 million transactions per second or not. But we all build applications in order for it to serve an end purpose for our users, to have some impact. And, we do that by listening to what our users want, one feature at a time. And in many places, we've seen, like specifically with our example of a number of applications we built at places like Facebook, we see that there is an inflection point. Suddenly, after a certain point, the applications simply take off, right? And you see yourselves in these kind of scenarios where you have accidental success, where the usage goes through the roof. That could very well be a million transactions per second. We actually have real world customers and users that are clocking a lot more than this in their databases using YugabyteDB. So let's take a look. So this 75 node cluster is serving writes at about a little over 2.5 milliseconds, and each read operation in about 1.2, 1.3 milliseconds. So the operations themselves are blazing fast, and they run, and the database right now is working on an over a 50 terabyte data set, right? So that's a pretty large data set with a huge volume count. And this data set is spread across 11 tables, 11 relational tables. This is, of course, our very successful retail application, e-commerce application that simply took off, right? So let's take a look at it. Now, what you have is firstly a number of tables. There's a customer table, there's your warehouses, your history of what your users have done in the past, your your items, and your orders table, your new orders, order lines, etc., and how many items you have in stock, right? And all of these are pretty big because obviously this e-commerce application really has taken off, right? So I mean, there's a few more tables, like there's a warehouse table and so on. Now, if you go look at let's go take a look at the metrics, right? What you see is that the application itself was running at a slightly lower scale, and as users started adopting it, you see that it skyrockets to a much higher count. At the current steady state, this application is performing application is performing about 472,000 inserts per second, about 312,000 select operations, 122,000 inserts, and about 15,000 deletes, right? And you can see the corresponding latencies. You see that the insert latency, the highest in this example, is about 6 milliseconds, right? And it depends on if the inserts actually have indexes or what it really does on the insert side, whereas the select and the deletes are about 3 milliseconds, and the updates themselves are 1.2. Now, the key takeaway here is that these operations are happening as a part of a number of transactions being issued by the end application. So the application is still the same transactional application that it was when the scale was much lower, except it's now able to handle it at a much higher scale. Okay, let's look at a few more metrics in this cluster. Well, what's interesting is, we're using about 60-65% CPU. So we still have headroom for growth, and we can always add more nodes if the usage goes even higher, right? And then what else is interesting in this cluster? Well, if you look at the number of operations, like the low-level IOPS per node, there's quite a few of them happening at a per node level, again with pretty good latencies. Yeah, nothing super interesting here. Yeah, you see that there's about 1 million connections, that RPC connections, that are being kept alive, and this is an example of where there's about, I think, 1.5 million client connections that are multiplexed into a smaller number of physical connections to the database. And yeah, the data set per table constantly keeps increasing because the application is running and it's doing stuff over time. Of course, it's deleting data as well that keeps it under check. You see that even though there's a high degree of cache hits, there are non-trivial number of cache misses. So the database is paging in from the disk as well, right? And you see that there's a number of new files being written, data coming in, compactions keeping up, and a lot of transaction, and there's some transaction conflicts happening as well, right? So all of this is being run as a distributed SQL database pretty seamlessly, right? Now let's take a look at what exactly is going on in the application layer. Well, the application is issuing a number of queries. And we see that here the queries are actually shown, right? you see a number of queries here. There's some inserts, there's some updates, and so on and so forth. There's a stored procedure call in order to optimize some of the things. There's an order line being updated, and we can even take a look at one of these queries. Like let's take a look at this. This particular query. Well, it says it's just a big insert into an order line for a particular order. Or you could take a look at, let's see, what are some other interesting queries? Well, there is a update of an insert of one of the order line where it presumably is setting the delivery date to change for a particular order ID. So somebody ordered some item and we're updating the delivery date, right? And you can take a look at your slow queries. You have, you can go ahead and take a backup of the whole cluster, even though it is a lot of data and it'll take time. You can create a scheduled backup, and the whole thing is being managed for you, like in the form, with health checks and so on. Now, remember that the database itself is built in such a way that it handles most of the operational tasks to make it highly available and make it very easy and simple to run. Okay, so that's the example of handling scale, right? Like you don't have to be afraid of that success anymore. Just go on and build that app and let your users use it and bring it on. Okay, great. So you saw that we actually hit 1 million transactions per second. No sweat, database able to handle it. You need more? Yes, you can get more. Now, you must be thinking, but how much scale do you really need? Is everybody going to be as successful as thelargestriver.com? Well, it turns out that we're seeing a lot of high-scale use cases. We have a single use case currently that is in production that's doing over 2 million transactions per second. Right? And workloads across the board frequently hit 300,000 transactions per second. This is pretty frequently. So yes, 1 million transactions per second seems pretty large to hear, but there's actually people that have more than surpassed it. As far as data sets go, 5 terabytes are no longer considered large. There's a lot of use cases out there that have about 5 terabytes of data. And there's a use case which has over 2,000 vCPUs in just one cluster. 200 vCPU deployments are pretty common. So when you're making those decisions on scaling up versus scaling out, keep some of these statistics in mind. Okay, now you obviously scaled to over 1 million transactions per second. That's a huge milestone in itself. You've unlocked a new level. You're now a Series C company with a $180 million Series C. Again, a ton of coverage, a ton more growth. Great. How are you going to evolve? Well, the elevator pitch evolves to a global everything else you were doing. So go global, go everywhere, go across the world, right? So the mission statement, once again, when the work begins, is now we're going to take over the world. We're going to give everybody the great experience across the world that we gave in the first region. Okay. So what are we going to do about that? Well, firstly, a never ever down initiative. And then, well, of course, you got to hire everywhere, which I'm just assuming is done for the purposes of this conversation because it's not about data. And as I said, we all know that's easy and that's sarcastic. It's the never down initiative. And we've got to operate in every major continent. And we've got to serve global users with low latency. So those are the critical things we focus on. Why? Well, it doesn't matter if a region goes down, anything goes down. Now that you have a big enough base and it's a critical enough service, you don't ever want to be down, right? The bad publicity it brings and the loss in revenue, everything is really bad. The second thing is the first step to going global is to operate everywhere, is to operate in the geographies that you need to. Why? Because compliance laws require you to keep data local for users. A lot of countries try to protect the data of their citizens and people living in their countries, and rightfully so. And lastly, nobody likes a global service that's really slow. A poor service with high latency is the quickest way to killing the service and the user experience. So you've got to move data closer to the end users. Okay, so once again, hello, distributed SQL. It solves exactly these things. The resilience ensures that entire cloud regions can fail and your database is still surviving, and therefore your app is completely okay. Obviously, this assumes that your application is also architected to be globally resilient. The second thing is about performance. And customers and users expect a snappy performance, right? Low latency, keep the data close to me, move it quickly. Nobody wants to wait on that spinning with a sign that says your data is loading and takes forever. And compliance is the third thing, where if you need to go global, you have to keep data local in some countries and process them locally according to the laws and regulations of that country. Okay, so all of that is too much to demo, but let's take a look at one of those things. Let's take a look at an actual regional outage, an entire region going out, and how we survive that. And by the way, for those of you thinking, how often does a region really go out, or an entire data center, how often does it really go out? Do I really need this thing? There's a couple of real world stories I can tell you. Last year, when the Texas snowstorm happened, a number of cloud providers actually lost power in their Dallas data centers, right? And this caused an outage for those deployments that existed there because there was simply no power to run the machines anymore. And for those people that had deployed it in a geo-distributed manner in order to survive failures, like some of our users had using YugabyteDB, they were actually able to carry on performing their transactional workloads off the other regions without being impacted by the regional outage, right? So we're living, even though this may seem far-fetched, it's not once you start growing into that scale. So without much further ado, let's take a look at the demo.
Welcome back. In this demo, let's explore high availability and fault tolerance capabilities of YugabyteDB. As you already know, a YugabyteDB cluster can survive rack level, zone level, and even region level outages, depending on your configuration. And let's take the most extreme scenario in this demo and simulate a cloud region failure and make sure that our application is not affected. I still use the same market orders application. The trades are coming from a public PubNub service, and we store those trades in our YugabyteDB cluster. Presently, that YugabyteDB cluster is running across multiple regions. I still have 3 nodes. Node 1 is running in US Central 1 region. Node 2 is located in Asia East 1 region. And the last, node number 3, is located in Europe West 3 region, a multi-region 3-node cluster. Every node is running on a dedicated virtual machine provided by Google Cloud Platform. And you can see it here, node 1, US Central 1, node number 2 in Asia, and node number 3 in Europe. Then, how do we simulate a region level outage? We're not going to ask Google about that. Instead, you can easily, for instance, simulate Europe West 3 outage by stopping this node. Let's do that. It's enough for our application. Okay, we are stopping the node, and as soon as Google Cloud Platform initiates the termination process, both node number 1 and node number 2 will determine that node number 3 is not available. And within a few seconds, they will start a new election procedure. As a result of that election vote procedure, they will become primary leaders for all the tablets that were primary tablets on node number 3. And in return, our application will not be impacted. Both node number 1 and node number 2 will be processing all the requests, even for the tablets that were previously primary on node number 3. So let's quickly go back to our application and make sure that it's still running. Let's wait. Okay, you can see that even though US West 3 region is down, I still receive all the trades and I insert those trades into my 2-node cluster. Okay, wonderful, good. Another thing that I wanted to show you. If I go back to Yugabyte platform, to this management screen, you can see that even though node number 3 is already down and all the requests are being processed by node number 1 and node number 3, it still said that it's live. What's happening? In fact, the cluster will give a chance to this node number 3 to get back. The cluster will keep sending heartbeats to that node within 30 seconds period or your custom period. And if the node returns, then it's fine. It will become a primary leader for its previous tablets. If it doesn't return within that time period, then the node will be officially removed from the cluster. Let's refresh that screen. Usually it happens by default within 30 seconds or minute. Okay, now you see that obviously the node has not returned, it's down, and it's unreachable. And it means that our whole Europe West 3 region is no longer available. But the application keeps running successfully. We can see queries, and those queries are being processed by two other nodes that are running into different cloud regions, like US and Asia. And final check, let's go to the application just to make sure that the logic is being executed. Yeah, no issues, you see? So what we've just done, we simulated a cloud region failure, and we confirm that the application is not impacted. Your application and your users, your customers can be served even during region level failures. Enjoy the rest of the conference. Bye-bye.
And that was a great demo, folks, of how one can survive an entire regional failure with pretty seamlessly, right? And this is one of the critical steps, as we have seen, to becoming a truly global company. Of course, there are other things like data locality and getting data closer to the end users. But anyways, the principle is pretty similar. Now, after having accomplished all of this, the largest river.com now really unlocks the next level and raises a $400 million Series D, and now starts opening physical stores. Well, you go online only to come back physical. And the elevator pitch evolves to, just take out cloud native. It's a global everything store with, of course, AI, NFT, Web3, and all that other stuff that actually gets you the funding. I'm kidding, of course. Okay, so new round, new mission. Well, the new mission is to be everywhere. Well, of course, we have to hire everywhere and become a much bigger company. But once again, let's assume that's super easy to do and, assume it's done. Well, the real technical initiative here is to become an omni-channel company. Every retailer is trying to move towards this and disrupt the in-store shopping experience. In case you didn't notice, disrupt is one of those words that's a very Silicon Valley word as well. Okay, so what is this seamless retail experience that we'd be designing? Well, a number of things that we're used to actually. Order in store and ship it to my home. So you go into the store, you take a look at the item you like, you really like it, you can touch it, feel it, see it, and you want it shipped to your home because it's bulky. Or maybe the store is out of those items in stock and they say they'll ship it straight to you. Similarly, the store wants to do a nationwide limited time blitz sales across all the stores in the website, right? Like an example of this could be, during COVID time, people want to stay protected and safe and really do the right thing for the community. So they drop prices on KN95 masks. Another example is to buy online and allow you to pick it up at the nearest store for, just convenience purposes. Retailers also want to do a lot of real-time analysis of holiday shopping in the cloud, like what is getting ordered, what is running out of stock, what is not being used much, what can they drop prices on, and so on. And lastly, there's a number of other applications, right? Like personalized shopping in stores, cash registerless checkout, a whole bunch of stuff. All right. So in the show don't tell policy, let's actually take a look at a demo of a next-gen point of sale system. Okay, so here we're going to do a demo, a show don't tell type thing of some of the retail experiences that we talked about. Well, we're going to talk about two specific retail experiences. And of course, our retail app right now is a microservices-oriented app. There's an API gateway, and we're going to talk about three specific microservices: the product service that deals with displaying all the products, the point of sale system or the shopping cart service, which allows you to add to shopping cart, and the checkout service that actually fulfills the order. Now, it really deals just with two types of tables. It's an approximation, but there's a product inventory and a product, but it's about two types of tables: the product catalog and the orders table, right? What we're going to do is one experience we're going to focus on is for the retailer trying to drop price from the cloud to the entire fleet of stores across the entire country, right? And this involves one-to-many replication. You make the change in the cloud, it needs to propagate all the way. The second experience we're going to focus on is that of the shopper. The shopper is going to place an order in the store asking the retailer to ship it directly to their home. So all of the shoppers are placing all of these orders across different stores. These need to be aggregated in the cloud in order for the retailer to have a bird's eye view of what orders need to be fulfilled. And this is many-to-one replication. There are many stores that has to replicate to a single cloud application. So let's take a look at this demo. Okay, first we got to understand the setup. The cloud portion of the e-commerce store is running on a managed database on AWS. I mean, remember, we started our mythical retail startup company on AWS. And each of the stores, we're going to talk about 2 stores. Of course, it's a simplification. There can be hundreds of stores here, but let's take 2 stores. And let's say store 1, that's what we're going to call it. And I'm going to switch to my terminal in a second. So we're going to color code these things. The cloud application is color coded blue and stores are color coded green. So store 1 is located far away from any cloud region in a remote location. And because it's not near any cloud region, it's running on a private data center that's living in the store. And naturally, Kubernetes is a really nifty way to do this. So it's going to be running on Kubernetes. Specifically for this demo, it's running on an Anthos cluster. And the second store is actually located near a Google Cloud region. And it's a fully managed, again, instance of YugabyteDB. Okay, with that set up, how are we going to accomplish scenario 1? Well, in order to broadcast pricing changes to all the stores instantaneously, and remember, these stores could get partitioned, so you still want them to work in a completely independent manner. We'll choose to use asynchronous replication of data, right? So the price markdown comes, let's say there's an item that's $158.74. We're going to mark it down to $100. Why not? Give the discount, see how many people buy it. Well, the minute you do this on the cloud application, on this particular microservice, it's going to change the price on a particular table. That table is going to replicate it all the way to store 1 and store 2. And store 1 and store 2's price is going to change from $158.74 to $100 even, right? And it's going to happen across the entire fleet of stores almost instantaneously. Then the second thing we'll do is a user, because of the dropped price, now comes and buys this item, right? So what's going to happen? Well, the first user is going to come to store 1 and place an order. And the second user is going to come to store 2 and place an order. All of these get pushed up to the cloud, and the cloud gets a global list of orders in order to fulfill. Okay, so that's what we're going to take a look at. All right, let's jump right into it. Well, first, what I have here is I have a React app, a UI-based app that is connected to store 1, right? And this is the online version of that store, because the physical version is far more inconvenient to demo. And we are going to be ordering something for the part 2 of our demo from here. Now, before we jump into this, let's go quickly to take a look at our setup. Now, if you folks can see, I have 3 terminals, right? Each of which is connected to a database. Terminal 1 is coded blue and is called cloud and is a connection to the database that's running in the cloud. Store 1 is coded green and is connected to the first store, which is a pretty remote store. And store 2 is connected to the second store, which is actually the local, like this is the one that's closer to one of the cloud regions. All right, so what are we going to do first? Well, the first thing we're going to do is we're going to update the price of a random item, okay? So let's first look at the prices. Well, I just picked 4 random items, right? I picked the SKU numbers of 4 random items. If you look at this query, it selects title, price, quantity, some stuff. It selects the actual inventory and it does a join across the products and the product inventory table and it prints them out. So what we notice is we have Cassell Standard Latin Dictionary, thumb indexed, selling for $158.74. But one point here, just to note, is that I personally would never buy a dictionary at $158.74. But if a lot of people are buying it, it kind of explains why the largest river is actually growing so fast. But anyway, that detail aside, and by the way, somebody remind me never to do a retail startup, but all of that stuff aside, Let's go run the same command on the couple of other stores. So on the cloud, and this is on a store, right, where it's the same price, it's $158, and there's 132 items in the quantity. And there's about 338 in total quantity across this store. Okay, now we want to drop the price of this item to $100. Okay, let's get on with that. So I now I'm on the cloud terminal, and I'm going to change the price of this item, whose Q is that, right, which represents CASL Standard Latin Dictionary, to $100 on the cloud side. Okay, having done that, let's check the prices, and we see that the price is actually reflected at $100. Now, let me go to store one, and if you remember, this price was $158. I go ahead and do the same thing, and I see that the price has dropped to $100. If I go to store two, once again, it was $158, and if I run this, it's now $100 as well. So great. As a retailer, we just updated and dropped the price of CASL Standard Latin Dictionary to $100. Of course, everybody would use Google today to figure out whatever the meaning of a word is, but we'll still stick to the thing that everybody wants to buy, CASL Standard Latin Dictionary. The only thing that was stopping them was the price being $158. Okay, now that we're at $100, well, let's go and take a look at placing an order through one of the storefronts. Well, the first thing that we'll do is let's look at all the recent orders that we've placed across the board. Well, if I run a command that looks at the recent orders and prints them in JSON format in the cloud, it shows there's no orders. If I go run the same thing on store one, it shows no orders. And if I'm going to do the same thing on store two, and there's no orders as well. So there are no outstanding orders in the system. Now, I'm going to go to the UI, because why not? And conveniently, there's CASL's Latin Dictionary, and that's the hot selling book that everybody wants to buy. If you guys don't have it, you should get yourselves one. But anyways, I'm going to get myself one. I'm going to add this to the cart. And I see that this is there in the cart, right? And I'm going to check out this bad boy. Okay, so I just ordered by connecting to store number one, the CASL's dictionary. And what we expect to happen, so what we said was users can go into the bookstore, into the actual physical store, they can browse it, they looked at the actual book, and now they place the order, right? And we're just doing it online, but they go talk to the storekeeper and they say, I want this book shipped home. All right, so let's go back, right? And let's rerun this query to see what orders there are. Well, and there you have it. There is actually an order for CASL Standard Latin Dictionary thumb indexed in store one. If I run the same query again on store two, well, nobody's ordered from store two, so there's nothing there. And if I go back, and the other thing to note in store one is if I run the inventory on store one, it's going to say like the quantity was 132 on CASL, it's dropped down to 131 because we've started fulfilling something, right? Now, if I go into the cloud and I want to see, show me all the recent orders that have been shipped from any of my stores, well, there you have it. The hot selling CASL Standard Latin Dictionary, right? It shows up right away. And so this can do a lot of things. Well, you can fulfill this from the cloud if the location of the user, if the home location of the user is really far away, because users can be buying stuff when they're visiting places. You could actually use this for analytics to backfill CASL Standard Dictionary. This could be useful for a number of things, as we talked about. So that's the demo in short. The point here is, we are reaching a stage of off-cloud and on-cloud type of experiences that have to blend, right? And there's a variety of different types of replication required, and we've used asynchronous replication in this case. But depending on the use case and the exact scenarios, we'd have to pick and choose the right tool. Okay, that was a great demo where we had an e-commerce cloud application, and we had one storefront that was very remote from any cloud region, another storefront that was pretty close to a cloud region, and how all of these things interact. So it truly gives a next generation and very seamless shopping experience, right, for the shopper. Now, is that all? Well, it turns out no good deed goes unpunished. So the more you do, the more your customers want, and it's actually a good thing. So some of the big trends in retail are the omni-channel shopping experiences, the shift to digital. How do you do partnerships with retail tech, personalization and mass communication, sending people coupons at the right time at the right place, security and customer privacy. And you have a number of such use cases around products and product catalogs and pricing list, order management, coupons, inventory management and supply chain optimization, customer identity, and foot traffic tracking and figuring out what positioning and location and display of your stores actually work. Employee scheduling for the people working at the store and messaging and so on. So there's a ton of stuff, right? And the largest river.com, let's say, actually goes ahead and starts tackling a whole bunch of this stuff. And thanks to the principles we laid out, they keep seeing success after success after success. Until the next step, of course, is to file for an IPO. Well, that takes some time. And it's not really about data. So while the largest river files for a IPO, you folks do check out these other great sessions over the next couple of days as a part of Distributed SQL Summit Asia. So sessions not to miss. Well, there's a fireside chat with Henry Aguda, who's the CTO of Union Bank of the Philippines, and he's going to be talking about transforming the financial industry in Asia. Bill Cook, our CEO, is going to be talking to Sue Chu, the CIO of MetLife Asia, about leading digital transformation. And again, remember, this entire session started with digital transformation and building cloud-native applications. Do check out this day 2 keynote with Josh Long of VMware about building reactive Spring applications with YugabyteDB. If you remember the tech stack, it was Spring. And then there's Kannan Ramamurthy of GM, who's going to be talking about harnessing the data from millions of connected cars. Now, why is this one interesting? We talked about 1 million transactions a second, and we talked about why that's not a big deal. Well, Kannan Ramamurthy is going to be talking about why they even had to exceed 1 million transactions per second in their use case of connected cars. And then there's James Hartig of Admiral, who's going to be talking about scaling YugabyteDB across 5 regions in 3 continents at Admiral. Once again, we talked about geo-distribution, a very similar use case. And there's a ton of other interesting sessions led by folks from Red Hat, Wipro, VMware, Hasura, HashiCorp, and a lot of others. So a lot of exciting stuff. Looking forward to it. And thank you, everybody, for signing on. Once again, I'm Karthik Ranganathan, the CTO and co-founder of Yugabyte, and hoping all of you really enjoy the Distributed SQL Summit Asia. If you want to get in touch with us, just join our community Slack, yugabyte.com/Slack, and holler, and here's our GitHub. You can check it out. Our code is completely open source.